2018 onwards. His area of research interests includes like dye-sensitized solar cells, and his group is actually working involving in development of low-cost and efficient materials for dye-sensitized solar cells, and mainly for the development of sensitizers, redox electrolytes, and electrode materials. As I told you, his research career is spanned about 25 years. He co-authored and published about 235 research articles and having 5,500 Google Scholar citations, H-index of 39, I-10 index of 125. He is very well-known, renowned scientist of the CSIR family, and he produced about 15 PhDs, and he has honors and recognized by fellow of Andhra Pradesh AP Academy of Sciences, Telangana Academy of Sciences, and he is a national coordinator for CSIR program, and he is fellow Luminescence Society of India, 2017. So with this introduction, I would like to I welcome Dr. Giribabu to speak on today's title of the talk is porphyrin-based dyes for dye-sensitized solar cells. Welcome, Dr. Giribabu. Please carry on. Please take the session and deliver his lecture.
Thank you very much, organizing committee, and thank you very much, Raghavaya, for a very warm introduction. And good morning, one and two all. Today, I am going to be present on porphyrin-based dyes for dye-sensitized solar cells. Okay. Porphyrins is, since the conference is mainly based on porphyrins and related compounds, and there is no need to any introduction regarding on this type of molecules. For dye-sensitized solar cells, I would like to present a couple of slides for the introduction. And just before going to the porphyrins, this is a natural photosynthesis. I hope all porphyrin chemists who is pursuing research in this area, they are well known about this slide. But let's see that I'll spend a minute on this slide so that what is the importance of porphyrins in this mechanism. Okay, natural photosynthesis consisting of a special pair of magnesium porphyrins, and where light is absorbed this special pair and then transferred to the excited electron transferred to the bacteria chlorophyll, from there to the bacteria phytin, and finally to the electron sinkers, that is the quinone type of molecules. So during this process, the carbon dioxide converted into the glucose. This is very well known anybody, but why I'm stressing here is that see in natural photosynthesis, porphyrins absorbs only the visible region. That is, porphyrin is having a storage band at around 420 or 450 nanometers, and Q bands from 500 to the 650 or 700 nanometers region. So, which means porphyrins in this system, porphyrins is having the absorption width in the visible region only. But whereas what happened is UV region. So that is the reason why the carotenes are present in the natural photosynthesis, which absorbs the UV light and transfer this excitatomic energy transfer to the special pair. So there is a wide spectrum of light absorption from UV region to the visible and up to the near region. So making such kind of molecules is not so easy in literature to absorb from the UV to the near region. So as a whole, what is that natural photosynthesis? Chlorophyll absorbs the light energy that converted into the chemical energy. So if you can use either natural dyes or artificial dyes which can tap the light energy, and then if you coat it on a semiconductor metal oxide, then there is a possibility to convert into the electrical energy. So exactly that is the contrast in dye-sensitized solar cells. The light energy is converted into the electrical energy, and whereas in natural photosynthesis, the light energy is converted into the chemical energy. Dye-sensitized solar cells belongs to the third generation solar cells, and I'm not going in detail about the various generations of solar cells. In general, silica family belongs to the first generation, and thin film solar cells such as amorphous, cadmium telluride, CIGS, etc. belongs to the second generation. And our day-to-day activity is based on the amorphous thin film silicon solar cells. But because they have its own disadvantages, that's why scientists is seriously working on the thin film solar cells and derived third generation solar cells. And once again, this third generation, which is also called as the excited solar cells, having a variety of technologies. Of these, Dyson size solar cells are at the verge of commercialization of the technology. So that is why people more focusing on the Dyson size solar cells to push further to the complete commercialization of the technology. And today I am going to be discussing elaborately, particularly on porphyrin based dyes for dye solar cells. Okay, it is a simple technology. Let's see that about its device fabrication and its working principle. So the device consisting of a simple glass substrate. General glass is non-conducting. To convert the glass into the conducting, coated as a chlorine doped tin oxide layer, so that non-conducting glass is converted into the conducting, onto which nanocrystalline titanium dioxide is coated by a simple technique, either a grade technique or screen printing technique. After that, the substrate is sintered at 500 degrees centigrade to evaporate the binders used in the TiO2 paste, so that the porosity of thin film titanium dioxide layers is found on the glass substrate. After that, the substrate is soaked into the dye solution, so that dye is absorbed on surface of a titanium dioxide. This is called as a photo anode. And similarly, we need to have a photo cathode also. A photo cathode is also nothing but the fluorine doped tin oxide glass substrate, onto which platinum is coated by using the spin coating technique. And after that, the photo cathode and photo anode overlay each other to leave the small space in between the two electrodes by keeping a small plastic substrate, so that a small space is leave, and also at the same time it avoid the short circuits. And in the space, a redox couple, generally it is the lithium iodide in organic solvents used for the redox electrolyte. After that, both the substrate is sealed it. Then this is a complete device. It is a simple device architecture, so that anybody can make this device, fabrication of this device, even in the undergraduate laboratory also. So after that, when you shine the light, what will happen? The dye is absorbed by sunlight, and then the electron in the ground state get excited into the in the excited state. From there to inject into the TiO2 conduction band. From there to the external load. At the same time, the oxidized dye get reduced by taking the electron from the redox couple, and the electron in the external load enter into the photocathode, and then the redox electrolyte is reoxidized, so that it completes a cycle. If the number of cycles are more, means that the durability of the device is very high. And then this is exactly similar to the natural photosynthesis, where the light energy is converted into the chemical energy. Okay. Then how to measure the efficiency of a device? If you want to measure for any photovoltaic device, whether it is a first generation, second generation, or third generation, the parameters are the same. So we need to have a short circuit current, which means that the maximum current obtained from the device at the zero potential, and we need to have the open circuit voltage, which means that the maximum voltage obtained at zero current. And then fill factor. In general, fill factor is the difference between the area within the curve and the area outside the curve. So, and then efficiency. Efficiency in general measured by the current into voltage by into fill factor by intensity of the light. So this formula is calculation for the efficiency of the formula is similar for all the photovoltaic devices. And this technology was first invented by the Professor Gretzel, EPFL Switzerland, and initially he used ruthenium polypyrrole complexes such as the either ruthenium bipyrrole complex. Generally, it is called as either red dye or N3, or a terpidal ruthenium complex is called as a black dye using the electrolyte lithium iodide in acetonitrile. And as on today, the certified efficiency of the device reached about the 11.9%. And another parameter which is very essential in the calculating the efficiency of the device is the IPCE, which is nothing but the external quantum efficiency. So IPC, the expand form is instant photon to the current conversion efficiency, which means that any dye molecule in the solid state has some broad absorption. So at each and every wavelength, how many photons are absorbing and how many electrons are leaving. For example, in case of red dye, at around 500 to 600 nanometers, it absorbs 100 photons and inject the 80 electrons to the TiO2 conduction band. If the IPC is more, means that more number of electrons are injected into the TiO2 conduction band. From there, it is converted into the electricity, which means that the efficiency of the device is also high. Okay. So what are the research directions in Dyson solar cells? As a whole, there are 4 or 5 different components are there in Dyson solar cells. The one is the electrolyte. In general, the electrode. In general, the electrode is the platinum-based one, which is expensive and less abundance in the earth crust. So that people are trying to use the different metals in place of the platinum, either metal complex based or carbon materials or other low cost materials. So the research here is also almost 10 because the carbon based materials has given their promising device efficiencies. And coming to the semiconductor metal oxide, in general, TiO2 is the people are using because of its biodegradability and vast available in the earth crust. So the research in this area is also almost came to the saturation. And next is the dye. Why we need to focus more on the dye? First of all, most of them we are the chemists, and the chemists can design a variety of dye molecules. So I will discuss more elaborately in the coming slide about the dye, and then coming to the electrolyte. And the electrolyte also we have to avoid the liquid electrolyte and then try to use either gel or solid type of electrolyte. And today I'm going to be elaborately discuss about the dyes, particularly on phosphine-based dyes. Okay. So what is the problem with the ruthenium complexes? When it's showing me about the 11.9% of certified efficiency, so anybody can think about the commercialization of the technology. The first problem is ruthenium is its availability in the earth crust. It's only the 6% availability in the earth crust, and lack of absorption in near area region. If you want to improve the further the efficiency of the device, then the photons in the near area region is going to be waste if you are using the ruthenium complex. And of course, it is having a labile NCS ligands. So the NCS ligands in this complex dictate the properties, optical and electronic properties of the complex, and which is very, very labile. So because of these technical problems, people are trying to avoid ruthenium complexes and try to use the either natural related pigments or organic dyes. But before going to the any dyes, that anyone has to keep certain points in their mind. Okay. The first one is that broad wavelength of absorption. So exactly in the natural chlorophyll, natural photosynthesis, where the carotenes and magnesium porphins absorbs from the UV region to the near area region. So we have to make such kind of molecules, but it's very tough. It's not almost scarce in the literature. And of course, it has efficient charge separation. If once the electron is injected into the TiO2 conduction band, then the dye should be sufficient lifetime in the oxidation state. Otherwise, it will be easily reoxidized by either by taking the electron from the TiO2 conduction band or from the electrolyte. And dye should have the redox potential, which will be matched to the TiO2 conduction band and reoxidized about the oxidation potential of the electrolyte. And of course, it is not the physisorption on the surface of TiO2, and it is a chemisorption, which means it has some strong anchoring group in the dye molecule. The new dye should be the thermally and photochemically stable, and which is durable up to the 10 years at an elevated temperature. And new dye should be soluble in all organic solvents and less hazardous. So anybody, if you want to pursue the research in the dyes for Dyson solar cells, one has to keep these points in mind and then design to choose the new sensitizers. Okay. But as on today, the ruthenium is still giving the better efficiency and better durability. And even the IICT also pursuing some research on the ruthenium type of complexes. But the red dye and black dye has given more than 11% efficiency, certified efficiency, but Z907 is showing the 8.3% efficiency only. But because of the two long alkyl chain presence in the molecular structure, it is giving the hydrophobicity nature, and at the same time, durability of the device is enhanced. If you look into the commercialization of the products, this is the first product released by the G24 company from UK, and they released a mobile charger in the year 2016, but they did not disclose about the material, what materials they have used in the device architecture. But I got an opportunity to meet the G24 people, and I personally requested then what type of materials they used. They have used the Z907 sensitizer, DAO2 semiconductor, gel type of electrolyte, and on plastic substrate. And they did not disclose, and they did not say that the durability and efficiency of the device, but still people are started buying this kind of products. So now our challenge is that if we can replace that in the commercial products with the ruthenium molecules with our porphyrin sensitizers, then the cost of the device is drastically reduced. Okay. So let's see that our group at CSIR-IICT pursuing all varieties of sensitizers. We are particularly interested in NCS-free type of ruthenium complexes. So we have successfully replaced all NCS ligands with the bipyridyl derivative ligands, and we obtained at around 8% efficiency. And even we are focusing on the non-ruthenium metal complexes like iron, but we got at around 1% efficiency only. And we pursued even on the pigment-based molecules such as tyrosines at around 3.5% efficiency only. And in the metal-free organic dyes, particularly very recently phenothiazine-based molecule, we crossed with efficiency of 10%. And natural molecules, once again, natural molecules like corals, we also pursued some research on corals, but the efficiency of the device it is around 1% only. And finally, we got very good results recently on porphyrin-based dyes, and we proved that these molecules even crossed the 10%. And recently, we got the 11% efficiency, and still we are not yet standardized those results. And I'm going to be elaborately discussed on the porphyrin-based sensitizers, how we started research and how we redesign the molecules. Okay, and since the Dyson size solar cells derived from the natural photosynthesis, and people thought that if you can use the chlorophyll molecules as efficiency.
Dr. Giribabu, your voice is not.
Let me. I used the maximum.
Yeah, it's fine. It's fine. Thank you.
Oh, okay. It has a intensified Soret band at around 420 nanometers and Q bands in about 500 to 600 nanometers. But when you did the literature during our started research, we had observed that its efficiency remained at around 0.2, 0.3% only. And moreover, if any chlorophyll molecule extracted from the leaf and exposed to the atmosphere, it will decompose very quickly, so that it will not useful directly as a chlorophyll extracted from the leaf. So we have to really design some sensitizers based on the porphyrin-based molecules. Okay, porphyrin is having the absorption an intense Soret band at around 420 nanometers, and if it is a free base, 4 Q bands between the 500 to 650 or 700 nanometers. So if you can push the absorption of porphyrin towards the red region, and at the same time, if you can improve the molar extension coefficient of Q bands, then there is a chance to apply the porphyrins to the Dyson size solar cells. Okay. Before starting our research, there is one publication in Journal of Physical Chemistry, and this one reported our great porphyrin chemist Professor Krishnanavi in collaboration with Rangel in 2000, and they observed an efficiency of 3.5% using the ideal redox couple. But if you use the free base porphyrin, then there is a labile protons are there in the molecular structure, and this will use, and what will happen as a cationic porphyrins in form, then porphyrin loses its electronic properties. So there is no use if it is a free base porphyrin. So what we have done is that if you want to keep the anchoring groups, there are the position on porphyrins, either the peripheral, that is the mesophenyl position, or beta pyrrole, or at the axial position of the metalloid metal or metalloid ions in the porphyrin cavity. Okay. Initially, we started with the by using the beta pyrrole positions by introducing the anchoring group. What we have done is that we directly introduce the carboxylic anchoring group to the beta pyrrole position, and you know that in porphyrins the electronic load is on above and below the porphyrin plane. So if you can introduce any substituents on the beta pyrrole position directly, then there is a pull the electronic load towards the TiO2 conduction band. And initially we thought that we have achieved efficient sensitizers, but when you apply these materials to the disolar cells, we got 0% efficiency. The reason is that when carboxylic anchoring group attached to the TiO2, and the TiO2 conduction band, TiO2 nanoparticles are very close to the porphyrin plane. So there is a chance of recombination of positive porphyrin plane with the electrons present in the TiO2 conduction band. Then we changed our design strategy by introducing the furan group, and then instead of the carboxylic acid, we introduced the cyanocarboxylic acid. The cyano group is a further electron withdrawing nature, so that there is more chances to the electron injection towards the TiO2 conduction band. And the efficiency is like in 0.1 or 0.2, and which is very, very low when compared to the ruthenium complexes. The reason here it is that furan is very bad conductor, one is, and second thing is also, which is not too far away, the anchoring group from the porphyrin plane. So the recombination is also, there is a chance here. Then we thought that we changed our design strategy by introducing the rhodanine acetic acid, and we can see that both at the beta pyrrole position and at the mesophenyl position, and we obtained an efficiency around 0.7%. Here the reason is that rhodanine acetic acid is a powerful electron withdrawing compared to the cyanocarboxylic acid, but the problem here it is that the conjugation is broken. Here it is that you see here it is nitrogen and then CH2COH. There is no conjugation. So if there is any, if you want to design any semiconductors based on the organic molecules, one should maintain the conjugation. If the conjugation breaking anywhere in the molecule, then it loses its properties. This is one of the reason in this design architecture, but there are some exceptions in the rhodanine acetic acid. But most of the molecules having the rhodanine acetic acid as giving the low efficiency. Then instead of that, we introduced a triphenylamine based molecules which are the powerful electron releasing, and then a simple phenyl carboxylic acid we introduced. You can see that the zinc porphyrin absorption is shifted towards the tritium at about 20 to 30 nanometers when compared to the zinc TPP, and also the solid band is broadened. And we can see that a broad IPC spectra we obtained from the 300 to 800 nanometers with the device efficiency showing at around 3.8, 3.3 to the 3.8. So we have added the CDCA co-adsorbent in the device fabrication. This is called as a quinodeoxypolic acid. Quinodeoxypolic acid generally is absorbed on surface of zinc porphyrin, so that it minimizes the aggregation during the anchoring onto the TiO2. So if you want to commercialize the technology of this kind of using this kind of molecules, one has to avoid using the CDCA co-adsorbent. See what will happen, this is the organic molecule. When you expose to the sunlight, this organic molecule is easily decomposes, and then the dye on the TiO2 surface started aggregating and it loses its efficiency of the device. So after that, so we have changed our design strategy by introducing a strong electron donor phenazine, and then we introduced the phenyl group, and then a triple bond and a carboxylic acid. So the triple bond will further improve the absorption in the near ear region. And you see that in the IPC spectra, in the previous case, the IPC is up to the 700 nanometers only, and here it is extended up to the 750 nanometers. That is the advantage of the introduction of triple bond in the molecular architecture. And you can see that the efficiency has reached up to the 5.4% efficiency, and which is almost a half when compared to the ruthenium complexes. But this is the highest efficiency reported by the meso substitutive porphyrins based dyes for disolar cells. But this is also not enough for the application of DSSC for the commercialization. So we have changed our design strategy. What we have done is that instead of that, we introduced a donor pi acceptor approach. Generally, donor is an organic molecule having the absorption in the UV region, and pi spacer is a zinc porphyrin, and acceptor is either a simple electron withdrawing natures like thiophene, benzothioazole, etc. And the anchoring group is either carboxylic acid and cyanocarboxylic acid we have adopted. And at the same time, we introduced the long alkoxy groups on the meta position of a phenyl ring of the porphyrin. I will discuss the importance of these alkyl chains in the coming slides. So in general, so what will happen after the electron injection from the porphyrin to the TiO2 conduction band, the hole is formed on the porphyrin get moved towards the donor molecule, so that the distance between the anchoring group to the hole has increased, then the chances for the recombination has minimized. So what we thought is that by adopting the donor pi acceptor approach, one can expect a double-digit number of efficiencies. In general, the donors is the organic molecules like carbazole, triphenylamine, etc., and the acceptor is either thiophene or benzothioazole derivatives. So this is the design concept. Adapted this design concept and made several perfume-based molecules. So first we introduced the either pyrene or carbazole molecules, and thiophene as thiophene, and then cyanocarboxylic acid as the acceptor. And then let's see that the efficiency of these kind of molecules in dye devices. And once again, we ended up with the 3% efficiency. Then we have gone back to the kinetics of these molecules and try to dig out the reasons behind that. And here we introduced a small methoxy group at meta to the phenyl ring, porphyrin macrocycle rather than the ortho position, and there is a still chance for the recombination of electrons from the TiO2 conduction band with the porphyrin macrocycle. And in the next design strategy, what we have done is that we introduce a long alkoxy chains at the ortho position to the porphyrin plane, and then instead of the pyrene or carbazole, we introduce the phenanthroimidazole molecules, which are the better electron donors or energy donors when compared to the previous molecules. And we have introduced the different alkyl chains so that the electron releasing ability of the donor will enhance. And let's see that this design strategy, and you can see that the absorption on the TiO2, particularly in the 500 to the 700 nanometers, has drastically improved. And moreover, the Q-band absorption here, in general, if you take the zinc TPP, the molar extension coefficient of zinc TPP at 500 or 600 nanometers is a few thousands, like 10,000 or 15,000. And whereas in our design strategy, the molar extension coefficient of Q-bands has drastically improved, and in some of our molecules, and it crossed even a lakh. So, which is very, very exciting results. And let's see that. And if you want to improve the absorption in the particularly UV region, and we have introduced an organic molecule, Photosynthesis organic molecule, so that the efficiency of the device drastically will improve. And you see that the IPC spectrum, and once again the broad absorption from 300 to the 800 nanometers is, you see that the first design strategy up to the 700, and second design strategy up to the 750, and in this design strategy the IPC extended up to the 800 nanometers. But you can see once again the efficiency is at about 7.5%. Of course, we have introduced a TBP, tertiary butyl pyridine, which is absorbed on the TiO2, sorry, on the zinc porphyrin to minimize the pi stacking during the absorption on the TiO2, and but the efficiency is still low when compared to the ruthenium complexes. So if you see, look into that, there is a dip at around the 500 nanometers in this IPCE. So if you can introduce a co-sensitization of a different molecule having the absorption in this region, then there is a chance to improve the efficiency of the device. So what we have done is we have introduced an organic molecule, and then you can see that the IPCE spectrum, there is a improvement in the absorption of the molecule at 500 nanometers, and at the same time you can see that the efficiency of the device is improved from 7.4 to the 8.2% efficiency. So which means that our design strategy is working well. So if we can further redesign the molecules, and there is a chance further improve the efficiency of the device, and particularly the new molecules should be the thermally stable, and for this reason we have executed the thermogravimetric analysis to understand the thermal behavior of our new porphyrin dyes. You can see that our new molecules are stable up to the 200 degrees centigrade. So which means that even if you use in the devices, if we use under the sunlight for a long time also, nothing will happen, because outside temperature is generally 45 to 50 degrees centigrade. So that is one of the achievement in the porphyrin dyes solar cells at the time. So coming to the different design strategy, and we introduced a phenothiazine, a powerful electron withdrawing molecule in place of a phenanthroimidazole molecule, and moreover the phenothiazine molecule is a butterfly shape and it is a non-planar, so that the aggregation is minimized in the sensitizer if you use it. And at the same time, for a systematic study, we change the different acceptors, and of course we know that furan and phenyl carboxylic acid based anchoring groups giving the low efficiency. But if you want to study the systematic kinetics, then one should have the different molecules. So we change from thiophene carboxylic acid to the thiophene cyanocarboxylic acid, and benzothiodiazole auxiliary acceptor groups, which are the powerful electron withdrawing. So these are the different molecules we designed and synthesized, and you can see that the absorption spectra in the solution, but in THF, the absorption is Q-band absorption is shifted towards a absorption maximum at around 700 nanometers, and the onset extended up to the 750 nanometers. And in general, which means that almost 100 nanometers of zinc TPP Q-band is shifted towards the red region, and at the same time, the solid band is also broadened, and its absorption maxima shifted towards the up to 485 nanometers. So this is also an interesting molecule, and let's see that its properties. So initially we have done the optimized studies, and let's see that its molecular structure, and long alkoxide groups that we introduced at the ortho position to the phenyl ring have covered on the above and below plane of the porphyrin. So it forms a alkoxide wrap over the porphyrin plane, which means that it avoids the recombination of electrons into the TiO2 conduction band. And at the same time, the phenothiazine molecule are present in the different plane from the porphyrin plane, which gives the non-planarity to the dye molecule. And we introduced a long alkyl chains to the phenothiazine, so that the solubility of the sensitizer will enhance into the different organ solvents. And you can see that the HOMO-LUMO levels, the HOMO is perfectly on the phenothiazine molecule and the LUMO is perfectly on the anchoring group. And in both the cases, HOMO is partially present on the porphyrin plane and LUMO is partially present on the porphyrin plane. So that we can expect the charge transfer from directly from the donor phenothiazine to the acceptor anchoring group through porphyrin plane. So that a continuous electron transfer be possible. And you can see that its energy levels, the LUMO is above the TiO2 conduction band and the HOMO is below the oxidation potential of redox couple, so that the electron injection from the excited state to the TiO2 conduction will facilitate, and it can reoxidize by taking the electron from the redox couple very easily. And you can see that the fantastic IPCE spectra, and this we reported and we got the patent also in 2017. At that time, this is one of the sensitizer having the thiophene cyanocarboxylic acid have shown the IPCE spectra from 300 nanometers up to the 900 nanometers. So this is one of the rarest molecule, a single molecule, not the co-sensitized molecule, a single molecule showing such a broad absorption in Dyson solar cells, which is very, very rare in the literature. And you can see even the IPCE has shown that above 80% from around 400 nanometers and up to the 800 nanometers. So over 400 nanometers, which means that 100 photons are absorbing and 80 electrons are releasing into the TiO2 conduction band. And by using these kind of molecules, we can expect a very good efficiency of DSC. And you see that, and we obtained it at around 10.2% efficiency. So, which means that we are very close to the ruthenium-based complexes. So, once again, I'm telling why stressing the ruthenium, because the simple ruthenium red dye and black dye, as if you look into the Aldrich catalog, they are selling about 70,000, 80,000 per gram of the molecule. And whereas this kind of zinc porphyrins, we can get even the couple of thousand rupees per gram. So that much cost difference is there. But the efficiency is very close to the ruthenium complexes at this moment. So let's see that. So if you want to commercialize, this is up to this is the academic interest of the research, because we are using only the liquid electrolyte. So if you want to push this kind of molecules to the commercialization, then we have to study the durability of the molecules in the device, not the thermal stability. Thermal stability, which means that isolated molecule, but in the device we have to understand about this durability. So for this reason, we have fabricated the device and replace the acetonitrile based liquid electrolyte with the methoxypropionitrile based liquid electrolyte, because the methoxypropionitrile boiling point is around 120 degrees and is less volatile compared to the acetonitrile. And what we have done is that we expose continuously the device to the light and then continuous heating at 60 to 70 degrees centigrade, and periodically we observe the efficiency of the device. As the time goes from 0 hours to the 100 hours, the efficiency is slowly enhancing. After that, it is slowly reducing over a period of 1000 hours. But when compared to the initial efficiency and final efficiency of the device, if the device is retained almost 90%, which means that these molecules in the device under the stress can survive up to a couple of years. So, which means these are thermally stable, and in the devices also, when exposed to the thermally and photochemically also stable. Next, see that how these molecules are stable towards the electrochemically. For that, what we have done is that why we need to have the electrochemical stability. See, in case of ruthenium complex, the ligand, the NCS ligands is highly level. So after injecting the electron into the TiO2 conduction band, ruthenium becomes oxidized. In the oxidation state, the NCS is easily replaced by the iodine present in the redox couple. So that if once NCS is replaced, then it loses its optical and electronic properties. So for that, we have studied about the spectral electrochemical studies. So what we have done is that we applied at its oxidation potential, and it's continuously we observe its absorption spectra. So if you apply the applied potential, in general, the Surret band is reducing its intensity, and at the same time, it forms another band at around 400 nanometers, and at the same time, the Surret band is reducing its intensity. So all these things. This study is not only giving its electrochemical oxidation, and it tells that the electron injection is from the porphyrin macrocycle, not from the zinc metal. Of course, this is well known in the literature about the electron transfer in zinc porphyrin. But if you once the applied potential removed, then it retains the original spectra, which means that our new designed sensitizer is thermally stable and photochemically stable and electrochemically stable with 10% efficiency. So there is a scope for the commercialization of these molecules, and we have scaled up this material from milligram to the 5 grams, and our CSIR has particularly sponsored a project on this scale up of this particular molecule, because CSIR is holding a patent on this molecule. And next, okay, up to that, 10% is not bad, and academically, we are very much interested to push our design strategy beyond the 11%. So next, what we have done is that in place of phenothiazine, we introduced the triphenylamine imidazole molecule, which is also a very powerful electron releasing group. And in the previous study, we come to know that either thiophenol carboxylic acid or benzothiodiazole based acceptor groups will give the maximum efficiency. So other anchoring groups will be avoided. That is the reason we minimize the anchoring acceptor groups in this design strategy. And let's see that its absorption properties, and you can see that the onset of the absorption in the solution state extended up to the 800 nanometers. See further red pushed in this new design strategy, and even on the TAOT absorption also, the absorption is shifted towards the onset of the absorption extends up to the 800 nanometers. So one can expect by seeing its absorption in solution on TaO2, and easily can tell that definitely it will further improve the efficiency of the device. And you can see that in particular in the 17 and 18 days, that is those dyes having the benzothiodiazole acceptor anchoring groups as giving the maximum IPCE, and the onset is extended up to the 950 nanometers. So the previous molecule has up to the 900 nanometers, and here we pushed up to the 950 nanometers. So definitely, and we can expect the very good efficiency. And even for in the IV current voltage characteristics also, our current has crossed the 20 milliamperes, because in the champion data, that is the ruthenium based complexes, with the 12% efficiency, the current is 21 milliamperes, which means that we outperform the ruthenium based dyes for at least in the current density. And even in our design strategy also, we crossed the 21 milliamperes current of the test cell devices. Okay, you can see that in the LG 17 and 18, the efficiency has reached up to the 10.5% efficiency. So, okay, even though we struggle a lot for the synthesis of a new dyes, but the efficiency has marginally improved from 10 to the 10.5% efficiency, but which is not a drastic improvement. But when you multiply the device area from test cell device to the mini module, this is nothing. But as academic point of view, this is a great achievement, and we can expect a good, even good publications also, even if you improve the 10 to 10.5%. Coming to the, okay, 10.5 is not bad device efficiency, but still our academic interest is going on to further push the efficiency of the device. So what we have done is that instead of a single donor molecule, we introduced a triphenylamine anthracene based molecule. These are the two donor molecules. Triphenylamine and anthracene are the complementary absorption in the UV region, so that one can expect the very broad absorption in this new design strategy. So we avoided even for the simple carboxylic acid as anchoring group, and we introduced only cyanocarboxylic acid. And we can see that from the beginning to the here, we are slowly avoiding some donors, some anchoring groups, and we are introducing the only efficient groups in the either in the donor or in the acceptor sites. And you can see that once again, here the Q-band absorption, onset of Q-band absorption extended up to the 800 nanometers, as usual in the previous case, but in the UV region particularly, and 400 to the 500 nanometers. So this is the combination of solid band of porphyrin and absorption of triphenylamine anthracene-based molecule, and can this. And even on the TiO2 absorption also, its absorption properties have improved. So by looking this kind of molecule, this kind of architecture, anybody can think about the further improvement of the efficiency of the device. And you see that here in the IPCE spectra, the absorption is further improved, and it is very close to the 1000 nanometers. So the absorption, you can see that the first 700, 800, 900, and 1000 nanometers. So this is also one of the rarest molecule having the absorption 300 to almost 1000 nanometers. And once again, even the current density also is crossed the 21.5 milliamperes. So as far as concerned to the current density is almost close to the ruthenium complexes, but unfortunately the efficiency is 10%, which is lower when compared to the previous design strategy. And then we are trying to find out the reason behind that low efficiency. And you can see that it's an energy level diagram. The problem it is that we are using the iodide redox couple in all our sensitizers. So the distance between the difference between the potentials of HOMO of dye and then iodide redox coupling is enhancing. At the same time, what will happen? The VOC, the open circuit potential, is reducing. In the previous case, it is causing the 700 millivolts, and whereas in this case is a 600 millivolts, around 650 millivolts only. So if you can optimize the redox couple, redox potential, then there is a chance of improvement of the open circuit potential, and then further improve the efficiency of the device. Okay. So far that we have find out the reasons behind that our design strategy, and we are continuously designing the new sensitizers. Instead of we took the phenothiazine based donor molecule, instead of the thiophene we introduced the thiophene, thiophene acceptor groups, and we thought that there is a chance to further improvement the absorption in the visible region, but unfortunately it does not improve the absorption properties, and the efficiency is further reduced. So I will discuss why it is minimized, reduce the efficiency of the device in my coming 1 or 2 slides. But here you see that the LG5 has shown the 9.6, and the new design strategy has shown efficiency only 8 and 7% efficiency. So in continuation of our efforts towards the different applications of porphyrin-based sensitizer, and recently we started by applying these similar sensitizers by hydrogen production, by utilizing the water splitting, and by using this molecule we got a reasonably good hydrogen concentration, and this is also the another application for our porphyrin-based sensitizers. Overall, you can see that in beginning, that is the 2010, we introduced the carboxylic anchoring group at beta pyrrole position, and we got 0% efficiency. And by changing our design strategy to donor pi acceptor, and we reached about the 3% efficiency. And we realized by introducing the long alkoxy groups at the other position to the phenyl porphyrin plane, then that is a forming of alkoxy wrapping over the porphyrin pi plane, and we reached up to the 7.4% efficiency. And by introducing the powerful electron donors such as the phenothiazine, non-planar phenothiazine molecule, and we reached up to the 10.2% efficiency. And by introducing the powerful electron withdrawing groups like benzothiazole based acceptor molecule, and we reached up to the 10.5% efficiency. And by complementary absorption of triphenylamine anthracene donor molecules, unfortunately, it got reduced to 10% once again. And with the reasons is that you can see that the energy level diagrams of all our design strategy as we go. For example, the triphenylamine imidazole based molecule, Lg18 got the maximum efficiency and the HOMO level is 0.94, and whereas the redox potential of redox couple is 0.35. This is common in all the sensitizers. You can see that in our Lg20 and where we observed only the 10% and the HOMO is enhanced to the 1.04 volts. And this redox potential is the same. So what will happen if we can tune this oxidation potential of this redox couple, then overall open circuit potential will enhance, then we can expect the efficiency of the device. But such kind of efficiency is possible only with the other redox couples like cobalt 2, cobalt 3 and copper 2, copper 3. And currently our group is focusing on the design of cobalt 2, cobalt 3 and copper 2, copper 3 based with the redox couples, and we reached up to the similar sensitization, reached up to the 11% efficiency by using the cobalt electrolyte, but still we have to standardize those device efficiency. That's why I'm not presented data. And I'm very thankful to my group where they are contributing mostly the synthesis and fabrication of the devices. And I'm also very thankful to my funding agencies like DST, CSIR, MNRE, Sunrise is Indo-UK collaborative research project. And thank you very much for your kind attention.
Yeah, thank you very much, Dr. Giribabu.
Yeah.
Now, actually, we are running out of time. Maybe we can take few quick questions.
Sure.
Yeah.
Shall I stop my sharing?
Yeah. No. Maybe if you want to look at your slides, somebody can point the slide.
Okay. No
the first question I can read from the Sanat Kumar Mahapatra.
Okay.
His question was, why that Soret band is broad in slide number 20?
Okay, see, it's broad and in the means in one design strategy, that is the triphenylamine anthracene is broadened. It is a absorption. It's a combination of absorption between the donor and porphyrin, not only the Soret band. In other cases, so there is a strong interaction between the donor and the porphyrin plane. So that is one of the reason it broadened the Soret band. So such kind of interactions you can see in the donor pi acceptor approach in all variety of molecules. Okay.
And Akila would like to know, is there any strategy to make an efficient dye? Means that architecture like best donor and best acceptor, or just its only trial and error method?
See, yeah. After the so much literature available, so one can understand that either thiophene cyanocarboxylic acid or benzothiazole cyanocarboxylic acid as acceptor groups, we are observing the maximum efficiency. Irrespective of whether it is a ruthenium complex or organic molecule or porphyrin or tyrosine, whatever it is. And in the donor cases, okay, if it is a porphyrin kind of molecules, I think non-planar donor molecules has given the better efficiency because of minimization of aggregation, like phenothiazine, triphenylamine imidazole, such kind of molecules. Yeah.
Okay. And Santosh would like to know, where is Santosh?
If I am right, he is clarifying the previous question. I think no need to ask.
Okay.
Maybe you can
And
go
Ruth would like to know how many days or hours are these dyes stable under light exposure?
Yeah, if you can see that the LG5, I presented all the durability data. See, thermally, those molecules are thermally stable up to 200 degrees centigrade, and even in the photochemically also it is stable up to the 1000 hours. So, which means that these are the reasonably good durable molecules when compared to the ruthenium complexes.
Okay. Yeah, I got the Santosh question. I am sorry. Santosh would like to know, dealing with acetylene group, is it synthetically easier? Double bond will bring isomer issues.
Yeah, so why we introduce the triple bond instead of the double bond? If we introduce the triple bond, there is a more chance to shift the absorption towards the red region. So that is why we introduce the triple bond rather than the double bond.
Yeah, I think with this I covered all the questions.
Sir, can I ask
yeah.
one question?
Yeah.
Please.
Yeah, quickly. In many of the device configurations, we constantly saw that when you increase the concentration of the dye, the efficiency was decreasing. Slide number 37, slide number 39.
So I never.
Yeah.
See,
so why is that?
I never presented about the concentration of dye in any one of my slides, but I told you that there is a additive in the electrolyte, that is a TBP, 4-tertiary butyl pyridine. See, we have to optimize the devices. See, the use of TBP is to control the zero current. Uh, and that is the one reason, and another reason is that the TBP is absorbed on the zinc porphyrin, so further minimizes the aggregation. In majority of organic dyes, as you go increase the TBP concentration, then there is an increase of device efficiency. And whereas in porphyrin sensitizers, either at zero concentration or 1.1 millimolar concentration, we obtain the maximum efficiency. So, which means that there is no need to add the co-additive in the redox electrolyte. That is one of the added advantages in our devices.
Okay.
So,
okay, I got one more question.
Dr.
Yeah, maybe
Raghav,
somebody
Dr. Raghav, I also have one question. Can I ask?
Please.
Okay, so Dr. Giribabu, let me congratulate you. I really enjoyed your talk. Excellent work. And I have a couple of questions. First of all, in all the porphyrin sensitizers, we see zinc is there. Why not other metal? What is so peculiar about zinc porphyrins?
See, for example, if you use the paramagnetic metals like copper, iron, then the singlet level is singlet quantum is very low. And why in the diamagnetic metals also zinc is very efficient. The zinc energy levels are well matched with the TiO2 conduction band, and at the same time, zinc single state lifetime is approximately 1 to 2 nanoseconds, and that is sufficient to inject the electron into the TiO2 conduction band. Because of these photophysical properties, zinc metal has given the highest efficiency when compared to the other metals in the periodic table.
Okay. So one more question. Have you tried any co-sensitizer?
Yeah.
Like you are making any your porphyrin devices?
Yeah. Co-sensitizer, see, if you are looking into the academic research, yeah, it's nothing wrong to use the co-sensitizer. But if you are thinking about the commercialization of technology, because I am from the CSIR, our office people, administration always ask, so how can we commercialize the technology? So if you want to commercialize the technology, the co-sensitization is not a good concept, because two different dyes absorb on two different strategies on TiO2 surface. So that is why, though the co-sensitization is giving a good efficiency, but when come to the commercialization, people are not adapting. So even in the same way, we also, our group also, not much interested on co-sensitization.
Okay. Thank you very much.
Yeah.
Raghu, can I ask a question? Is there some time? Giribabu sir, this is Raghu. Good morning.
Yeah.
Yeah.
Go ahead.
So it's an excellent talk. I mean, I was coming and going because of some internet problem, but it was excellent talk. I listened to this at least few of them before. So I have one question, even though I'm little closely observing your results these years. But what? Let's say if you, I mean, ruthenium. The best of ruthenium is its triplet state because the lifetime is very high for ruthenium.
Yeah.
So, what do you think, like for porphyrin compounds, how to increase the lifetime? To add secondary donors, that is one of the idea, or I think we should go for different metals, like what Dr. Iti was saying. What do you think will be a better way to approach for to increase the lifetime of porphyrin? Go for secondary donors or different metals?
See, for example, as far as concerned to the porphyrins, ruthenium metal in the porphyrin cavity will not work for the dyes, first of all, and
Yes.
yeah, will not.
And it is expensive. If it works, yeah.
Not only the expensive. See, forget about it. If you want to pursue the academic research, forget about the cost initially. See, the problem it is. Why ruthenium polypyrrolic complex giving the maximum efficiency when compared to the other metal complexes in the periodic table? The efficiency contribution coming from both singlet and triplet states. And similarly, if you use the ruthenium porphyrins, the efficiency coming from the only singlet state, not the triplet state. And coming to the donors part, yes. Any organic molecule having the powerful electron releasing groups and non-planar in nature, you can use it. That is nothing wrong. That is why, particularly for triphenylamine derivatives and phenothiazine derivatives and imidazole-based derivatives has giving the highest efficiency when compared to the other simple donors. And our group has used the other donors like. I did not present the lack of time, like phenothiazine, not only phenothiazine, like carbazole, pyrene, anthracene.
Sir, 1 minute, sir.
Yeah.
Mr. Sanath, you are presenting. Mr. Sanath, we have to remove you. Please stop presenting.
Yes,
just remove him. Just remove him. No mess.
Okay, sir, you carry on. I will do that, sir. You please.
We can't see the screen.
Yeah.
We can't see Dr. Giribabu's screen.
Yeah. Any.
I think already have done.
Yeah. Any non-planar donors, you can use it as the donors case. So planar donors.
I have one question, sir. At this point, like, too big of a dye is also bad for TiO2. And too small, lifetimes are not that good. So what do you think with your experience? How many donors you can put? Like maybe 1 or 2? Like what is your empirical experience? I mean, empirical rule that comes from your experience?
Yeah, that's a good question. We have to optimize even the size of the molecule also. So that may be the one of the reason that triphenylamine, anthracene, because of molecular size is enhanced, and even the quantity of absorbed dye and TiO2 is also reduced. So to best of my knowledge, the phenothiazine is the ideal in terms of efficiency and quantity of dye absorbed and TiO2 surface and the size of the molecule also as a whole. It's an optimum molecule. So if you can further push the efficiency of the device by changing the electrolyte, I think that is the better one.
Can I ask one question?
Thank you, sir.
Yeah, go ahead.
What is that?
Giribabu, this instead of zinc, if you want to use tin,
yeah,
do you think that tin abundance is also good, and you can do through axial ligation, you can also protect the this recombination?
But yeah, that is true. But you see the photophysics of tin and zinc porphyrin, because I had experience of tin porphyrin during my PhD time. In general, the quantum wheels are less, singlet state quantum wheels are less when compared to the zinc porphyrins, and even the lifetime is also low when compared to the zinc porphyrins. So that is the reason. Zinc porphyrins has the optimum photophysical properties. That's why it's giving the more efficiency. Otherwise, if you use the tin, the axial ligation is there, and then one can expect the minimization of aggregation on TiO2 surface. Then you can get it. But as on today, tin porphyrin has giving very low efficiency, not even 1%.
Okay. Thank you.
Can I ask one question?
Yeah,
Yeah,
go ahead.
maybe this is the last question, Dr. Gokul.
Only
Please.
one.
Yeah, please.
Sir, you told in one of your slide, you mentioned about the co-synthesizer. That means HC5 you added, so that you can get some of the whatever the absorption spectra you missed, you could able to regain it actually.
Yeah.
HC5. What is the absorption profile of that alone, that molecule only?
See, I used the small molecule as a co-sensitizer.
Yeah.
You can see that in the IPCE spectra at around 500 nanometers, there is a dip in the IPCE spectra.
Yeah.
So if you can improve the IPCE at that nanometer region, then there is improve the efficiency of the device. So that is why we use a small organic molecule having the absorption at that particular wavelength region, and the device efficiency also increased from 7.4 to the 8.
Will absorption, sir, that's okay. Will absorption spectra and IPC spectrum, are they linearly correlated, or how? Because often it never mismatches, right?
No, see, absorption spectra on TiO2 surface and IPCE you can correlate. You can correlate.
Correlate. Will it give,
you can correlate.
Will it give a symmetrical? Will it give a close profile? Close profile.
Yeah, most of the cases, at least 90% is the close profiles. Maybe 1 or 2 exceptions are there.
So I always get the same doubt actually. This is my curious question. Whenever you
No, you always compare the absorption of dye on the TiO2 and IPCE you compare, and you will get almost 90% is similar.
Oh, that means whatever we see in the absorption, that understand, sir, understand. Whatever you see in the solution absorption, we cannot make out that this dye is qualified or not, right? We cannot make out.
No, see, for example, forget about the dye molecule. You take any molecule absorption spectra in solution in solid state. Do you think that is a similar? Because of in the solid state, there is a chance between the pi-pi interactions or van der Waals forces, etc.
Yeah,
and the broad will form.
Aggregation.
Yeah, broad spectra will form. And similarly, on TiO2 also, we cannot expect a similar type of absorption spectra as we observed in the solution. But you can expect that if the absorption is very broad in solution, and we can expect a further broadened absorption on TiO2.
Okay. Yeah. Okay, sir. Thank you.
Shall I stop sharing?
I think you already stopped. We cannot see. Yeah, we can see.
Yeah, I stopped it by sharing.
Sir, can we move on to Dr. Gokul?
Yeah. Thank Dr. Giribabu for your excellent talk, for presenting your wonderful results.
Can we please just clap?
Thank you very much. Thank you very much for your kind attention.
Thank you, sir. Thank you.
If anybody has any doubts, drop a mail so that I will try to convey my level.
Thank you, sir.